Hi guys, so in this video today we're going to take a look at modelling problems using exponential equations. And we recall that exponential equations, or simple exponential equations, are those of the form y equals a to the power of x. We remember that if little a is greater than 1, then we have a series of values that becomes greater over time. So we have what is called exponential growth. This is a very good model for things like bacterial growth, population growth, and many other examples in nature. If little a is less than 1, then we have a series of values that become smaller and smaller over time. And we talk about this being exponential decay. The most commonly encountered example would be radioactive decay, but we can also see exponential decay in the difference between the temperatures of two objects. So if a hot object is placed into, for example, cool liquid, then the difference in temperatures between the liquid and the object follows an exponentially decaying curve. In all of these examples, the capital A in our equation is our initial value. It's the value when x is 0. So if we had a population that began with 10,000 members, so we'd have A equals 10,000, and it was experiencing growth such that, say, it was increasing by 5% every year, then what we have is we have a growth factor of 1.05. 1 so that we've still got the initial population, and the 0.05 so that it's grown by 5% at the end of each year. And then we just have t equals years. And so our formula would be that the population after t years would be given by a to the power of t, and in this case that'll be 10,000 times 1.05 to the power of t. So every year that population is going to get 5% bigger, and that's going to happen again and again and again. But of course, that gives us a geometric sequence for what the population is at the end of each year. But being an exponential equation, we can actually evaluate this at any point. I can say, well, what's the population going to be 3 months in, 5 months in, 1.5 years in? As another example, let's look at decay of a radioactive element. So we start with 10 grams of radioactive material, and it decays in such a way that at the end of every year 1% of the total mass has decayed. And so what this means is that our growth factor, in this case our decay factor, is 0.99, because of course we have to say how much of the material is still there. So if 1% is decayed, 99% is still there at the end of each year. And that gives us that the mass over time of this radioactive sample is 10 times 0.99 to the power of t, where t is our number of years. This, of course, gives us an exponential decay curve that looks something like this. Okay, so it'll decay over time, slower and slower, asymptoting towards 0. An interesting question about radioactive elements, though, is this idea of half-life. At what point in time is there exactly half of the sample remaining? So we would call this t half. And so it turns out then that what we're trying to solve is when exactly does this reach 5? If we started with 10 grams, so 0.99 to the power of t equals a half. Eventually we'll have the mathematics to actually solve this exactly, using logarithms, which we'll cover in the next video. At the moment though, we'll have to resort to trial and error. And by trialing different values of t, we actually find fairly quickly that when t is equal to approximately 69, we end up with 0.99 to the power of 69 being a half. So for this particular radioactive element, 69 years would be stated as the half-life. After 69 years, half of the sample remains. After another 69 years, it's halved again, so we've now only got a quarter of our original sample. Some radioactive elements, for example carbon-14, which are used for radioactive carbon dating, have half-lives around the order of 5,000 years, which means that over the course of 5,000 years, half of a particular sample will decay, and after 10,000 years, you've only got a quarter left.